Hey everyone, welcome to this video on partition coefficients. I'll be explaining what the partition coefficient is and how we go about actually applying it to some of the concepts we've been seeing in our course. So let's get started with the partition coefficient. Great. So the partition coefficient describes for any molecule, okay, any molecule. And that can include salt, sugar, any kind of molecule that we want to think about. We know that it has some inherent solubility. And this varies. So it's actually solubilities in different solvents. Let's think about that. So if we put salt, let's say in water, we expect it to be more soluble than if we're putting it in oil, right? Water versus oil, right? And that tells us how soluble, and we expect to see a higher concentration of dissolved salt in water versus oil, right? And this is where the partition coefficient comes in. When we have two different solvents, the partition coefficient tells us how a molecule, such as our salt or sugar, any molecule, how it partitions itself between the two solvents, okay? So how a molecule partitions itself between two solvents. And this is also at equilibrium, okay? At equilibrium. That's the key part. So what does it mean at equilibrium, right? That a molecule partitions itself. Well, let's think about this. We have two different solvents, okay? Let's say we have water on one side, and on the other side, we've been talking a lot about membranes, right? So we can say this side, well, let's say it's the membrane, okay? What is a membrane? Well, it consists of lipids, right? So we have, it's kind of a fatty or oily solvent, right? Well, let's use our salt example. And if we have salt in water, we expect a lot more particles dissolved in the solvent, right? It's more soluble in water than it is in oil. We expect less particles, right? A lower concentration. But the thing is, this is at equilibrium, right? At equilibrium. At equilibrium. This means that we have, right, more soluble salt molecules in the water, right? We have more of salt. We have a higher concentration in the water than in the membrane. But it's at equilibrium, right? How do we actually quantify this difference in solubility? We aren't saying that, well, there's a bigger drive over here. It's the same amount of molecules, but actually it's more soluble in water than it is in the oil, okay? So let's think about this a little more. So at equilibrium, right, we know at equilibrium, we know that, well, let's say our molecule X, right, salt, in the water phase is at equilibrium in the membrane phase, okay? Well, we know then we've been talking a lot about equilibrium constants, right? We can define the equilibrium constant K, to equal the concentration of the reactants, right? Or in the membrane over the concentration in the water, right? We know it's at equilibrium. But we know that because salt is more soluble in water, we expect to see a higher concentration in water than in oil in the membrane. Okay, we're going to keep solidifying this concept as we go throughout this video. And this is the definition of the partition coefficient. So this is actually the partition coefficient. And this is the Greek letter phi, right? And this is the partition coefficient. It tells us the difference in the concentrations of the same molecule. We use same molecule X, right? Same molecule, but in different solvents, right? We have solvent number 2, solvent number 1. Okay? Now, let's actually talk about 3 different cases, right? 3 different cases. This is a very simple concept, okay? 3 cases. So just stick with me. We have 3 cases. Well, the first case, right? Simply, we have a higher concentration in water. I'm going to just denote by W, right? And it's going to be greater than the concentration of the membrane, okay? Denoted by membrane. Actually, I'll write it out because they look very similar. Okay, concentration water over concentration membrane. This means that the partition coefficient K, right? We defined it earlier as membrane over water, right? So we have membrane, I'm going to actually just simplify here, over water, right? And that means if we have a bigger number in the denominator and a smaller number in the numerator, we know that the partition coefficient is going to be less than 1. And less than 1, we also describe this as unity, right? 1 is unity, okay? Here's our second case. Our second case, you can already guess, it's going to be when the concentration in the water is less than the concentration in the membrane. And this means with our same definition of partition coefficient, which is simply just saying the same molecule in 2 different solvents. And we're comparing just the concentrations because of the difference in solubility. Okay, and it's at equilibrium. Equilibrium doesn't mean the actual concentrations will equilibrate to the same number. That's not true, right? Instead, we're saying, well, the flux to one side and the flux to the other side are equal but opposite, right? But the concentrations are different because of the different solubilities. That's based on the property of the actual molecule, right? And the solvent that we're actually looking at. So let's keep going. So we have the membrane over the concentration of the water, right? And in this case, we have a higher numerator and a smaller denominator. Well, you guessed it, this makes K, our partition coefficient, greater than unity, right? Greater than 1, unity. It's simply just saying, well, the numerator is greater than the denominator, right? And as you can guess, our third scenario, our third case is if these concentrations are equal. Okay? And this means based on our definition earlier, right? They're equal, right? Meaning that K is equal to unity, right? Equal to 1, okay? So this means that there is no difference in the solubility, right? Let's actually talk about this in the bigger picture. What does the partition coefficient tell us, right? What does the partition coefficient tell us? It tells us qualitatively, right? It's a qualitative assessment. It's a qualitative assessment of which molecule, right? Or which solvent the molecules actually dissolve better in, right? So of whether the molecule in question, right, dissolves better in solvent 1 or solvent 2. Right, let's scroll up just a little bit. So if we know that it dissolves better in the water than the membrane, we expect the partition coefficient to be less than 1. And actually, if we know that the molecule dissolves better in the membrane than the water, we expect K to be greater than 1. And if they actually dissolve, right, that solubility is equal, then we expect it to be at unity, okay? So that's the main idea of the partition coefficient. It compares the solubilities of the actual molecule in different solvents, okay? And here's the second thing that it tells us. Well, it addresses discontinuities in concentration profiles, okay? And we saw this actually in quiz section, right? But let's take a step back and let's think about it. Well, we just looked at two different types of actual conservation in this course, right? We first looked at heat transfer is one of them, right? And our second one is diffusion. So we looked at both of these, right? And why do we not care about, why did we not talk about partition coefficients in heat transfer, right? Why? Well, because heat transfer deals with temperature. We're solving for temperature, the temperature profile, and we know temperature is continuous across different layers, right? Although the case might be different, the temperatures will always be continuous, right? We define it as a continuity variable, right? But on the other hand, for concentration, as we just talked about above, concentration is dependent on the actual solvent, right? If we have a solvent that actually allows for higher solubility, we will have a higher concentration. And there will be a jump. Let's actually take a look. So if we have, right, K1, material K1 and K2 in our heat transfer, right, we would expect to maybe see some heat transfer like this and maybe kind of the smaller slope, right? But still it's continuous right here, right? But on the other hand, concentration, right, we can have in solvent 1 and solvent 2, we could expect to see maybe like it's decreasing a little bit on this end, and then it goes like this, right? Something we've seen in quiz section. Yeah, maybe I'll make this slope a little bit more slanted, right? And this jump is explained simply by our partition coefficient, right? If we see this concentration, these black lines are concentration profiles, okay? So we can see if there's a higher concentration here on the left-hand side than the right-hand side, right? And this jump, discrepancy, we can expect the solubility to be higher. Okay, solubility is expected to be higher and lower. Okay, and the partition coefficient basically accounts for this discontinuity. Okay, that's the definition of a partition coefficient. All right, so we saw this question in quiz section, but I do want to go over it. This is from Chusky 6.7. So let's actually read the question together. An uncharged membrane separates two aqueous salt solutions. Okay, so we have two aqueous salt solutions, and it contains a protein at concentrations Cl and Cr, simply concentration left and right, right? Left and right concentration. left and right. And we know concentration left is greater than concentration right. And stirring the solutions reduces but does not eliminate mass transfer effects near the membrane surface. Great. The salt concentrations are the same for both solutions. So we're actually talking about, right? The protein concentration is the key, right? Protein concentration, but it's saying the salt concentration is the same. So it means essentially the same solvent on the left and right-hand side, okay? So what is the actual different solvent? We were talking earlier, we were talking about two different solvents, right? Well, simply, it's the membrane, right? The membrane. The membrane is that second solvent. So we have solvent 1, solvent 2, and back to solvent 1, right? Great. So now, let's keep reading, right? Potential differences are negligible. And we have the concentration distributions in these black and red lines. So this is also a concentration gradient, right? The distribution. So it says for each sketch, briefly discuss whether the concentration profiles are physically possible, okay? And if they are, determine whether the partition coefficient is greater than, less than, or equal to unity. Unity meaning just 1, okay? So let's actually take a look at these case by case. And let's really talk this through, okay? So we have, for our first example, we have our membrane right in the middle, right? We have the membrane, and then we have Cl and Cr, and Cl looks like this, and then we have Cl or Cr down here, and then we have the membrane looking like this, the concentration that matches above, okay? I'm just copying this. Okay, so let's get started. So we're like, oh my gosh, we have now three different layers, right? We were just talking about 2, but actually no, we talked about this is solvent 1, this is solvent 2, and then this is solvent 1. This is simply just going back to the same solvent. So how do we write the actual partition coefficient? Well, it's right at equilibrium, K is equal to, right, the concentration in the membrane over the concentration on the left side, right? This is, remember, it's a solvent 2, solvent 1, yeah? And this is at the actual interface, right? This is at the interface. So let's actually take a look. So we have right over here, Cl ends right here at the interface, and Cm is down here. Well, which one is smaller? Definitely Cm, right? Cm is smaller. That this point is lower than the top point, right? So that means Cm is going to be less than Cl. And this tells us the partition coefficient is what? Is less than 1, because the numerator is smaller than the denominator, okay? Now let's do this again for the right-hand side at this interface, right? And if we keep the same, right, we said number 2 is on top and number 1 is on the bottom, right? That's just how we've been writing it out. We have K is equal to, again, Cm over Cr, right? Solvent 1, right? Simply, remember, this is the solvent 2, solvent 1, okay? So if we take a look here, we have Cm is down here and Cr is up here. So again, we have Cr is greater than Cm. This means that K is also, the partition coefficient is less than unity, less than 1. Because we have the same solvents on both sides, right? And we have the membrane, we expect to see the same sign in the partition coefficient, right? We're saying, based on the definition of the partition coefficient, this protein, right, is less soluble in the membrane than it is in the salt solution. So we have to definitely see the same K sign, right? The sign of the K. We need to see this. So because they match, it's good, right? But there's one more way to confirm this, okay? There's one more way to confirm this. And it is through what we just talked about in quiz section 2, flux. Oops, flux, right? Diffusive flux. We know that flux of any molecule is from high to low concentration. So if we look here, we have a higher concentration here and a lower concentration here. So we expect flux to go to the right side, right? The right-hand side, left to right. And in the membrane, we see it going from high to low, right? So we expect it to go, again, left to right. And then here on the right-hand side, we have high to low, okay? The flux, again, is going in the same direction. So by our flux analysis, right, we also confirm that, yes, it's going in one unified direction. So this is therefore true, okay? Partition coefficient is less than 1, and this concentration profile in the membrane can exist, okay? So we need both the K and the flux to determine this, okay? Both the partition coefficient and flux analysis, okay? Now let's try our second scenario, okay? So now hopefully we have a better hang of this. So why don't you try pausing the video and try to work it out, right? Try to work it out. So we have Cl, Cr, and Cn. So why don't you pause the video and try it out, and then unpause when you're ready. Let's get started. So we have, right, let's redefine our partition coefficient. Again, it's the same definition, Cm over Cl, right? The concentration in the membrane over the concentration in the left-hand side, right? And we can see clearly Cl is smaller, right, than Cm. So here's the difference, right? We have actually the partition coefficient is greater than 1 here. It says, well, the protein is more soluble in the membrane than it is in the salt solution on the left-hand side. Okay, well, let's check the right-hand side now, right? So we have Cm, let's first define partition coefficient again, Cm over Cr, okay? And we can see here, well, Cr is right here, and it looks like it's greater than Cm, right? Cm is smaller here. So here we have the partition coefficient is less than 1. It says on the right-hand side, the protein is more soluble than in the membrane. And that does not match. These don't match, right? These are opposite statements, right? We just said on the left-hand side, it's more soluble in the membrane. And then here we say it's more soluble in the salt solution than the membrane. That can't be true, okay? So because of this mismatch, we know that this concentration profile in the membrane cannot exist, can't exist, okay? Let's also do our flux analysis, right? Let's do our flux analysis. So flux analysis tells us we have high to low, right? So we have flux going to the right-hand side, right? Left to right. And also in the membrane, we have it going from left to right once again. And then here we have high on the right-hand side going to low, right? So that means we have flux going to the left-hand side. And now we have a mismatch in flux, right? We need flux to be going in one singular unified direction, right? So because of this mismatch, we know by our flux and our partition coefficient analysis that this concentration profile and also this right-hand side, it just can't exist, right? That's how we know that. Okay. we're going to do part C now. So if you didn't pause for the second one, please go ahead and pause the video and give it a try yourself. This is really good practice, okay? So let me just draw it out. We have CL, and then we have CR, and then we have our CM, okay? And hopefully just by looking at it, we can already know, right? So let's define K once again is CM over CL. And then we have K is equal to CM over CR, right? We defined this 3 times now, 4 times. So hopefully we understand that we're just comparing 2 different solvents and this protein solubility in these solvents, okay? Not rocket science. So if we take a look, CL is greater than CM. So we expect K to be less than 1 because the denominator is bigger. Okay, and then if we check here, Km is greater than CR, right? CR is much lower. And that means we have K is greater than 1. We have the numerator is bigger than the denominator. And we have yet again a mismatch, right? The left-hand side says, well, it's more soluble in the salt solution. And the right-hand side says it's more soluble in the membrane. We have a mismatch in the partition coefficients. And let's do our flux analysis one more time. Flux, right? We have high to going to low, right? So we know it's going to the right-hand side. And we have here low to high. So we know it's going to the left-hand side. Okay, well, already we have a mismatch. And then we have high to low, right? Going this way. So then we have flux going this way. And this cannot happen. Do we have some generator over here? That's not true, right? We don't have something that's generating these proteins at this interface. So that cannot be true, right? So we have a flux mismatch and a partition coefficient mismatch. Okay. So we know this concentration profile cannot exist. Okay. So this is one type of question that we can see on partition coefficients, right? And another question that we can see is actually how we can derive an expression for the concentration profile in the membrane, right? Using partition coefficients. Let's take a deeper dive into this, okay? So this is 6.8. So this is following 6.7. And this is referring to section 6.7, not the previous question, okay? Not previous question. Okay? So let's read this. Diffusion through multiple layers of tissue arranged in series was examined. So it's saying, well, this is tissue 1, and then this is tissue 2. Down here, sorry, it's hard to see the red. And it says, now consider steady state diffusion, so zero accumulation, through 2 media arranged parallel to each other. And we're assuming that diffusion is one-dimensional, and that makes things easy. That makes life easy. And we're given some boundary conditions. But before that, first, I want to make some simplifications for this question. And let's say, let's only look at one layer, okay? So let's simplify to 1 layer, okay? So that means we're just not going to look at this, yeah? And we're just going to look at the top. But now I'm going to make this a little bit more challenging. So let's try, I know this is in rectangular coordinates, let's try cylindrical. Okay, let's try cylindrical. And we're like, whoa, no, I don't want to do cylindrical. Well, just stick with me, all right? We'll actually see. So we can see in this diagram, we have C0 and CL. We have 2 different concentrations. So we have different, right? This is actually the same solvent, right? Solvent number 1, right? And then this is solvent number 2, okay? So it's the same thing, yeah? Let's not be worried about this. So I'm going to actually redefine some variables, and because this is rectangular, so let's actually draw this out. So in cylindrical, we expect to see an inner layer, right? An inner layer. So we have an inner layer here. And then we have a middle. And then we have an outer layer, yeah? So we're going to say, well, this is going to be C1, right, at this interface. And then this is going to be CM, the membrane. And then we're going to say this is C2, right? And this is going to be, instead of saying 0 and L, right? Instead of saying 0 and L, we're going to say, well, this is going to be R in, okay? And this is going to be R out, okay, in cylindrical. This means let's redefine our boundary conditions and let's use our partition coefficients to understand, right? The partition coefficient, right? The definition, let's actually write it out, right? The partition coefficient, let's say at when R is equal to R in, right? Let's look at the difference right here, right? We said, well, the partition coefficient is equal to, we said Cm, right? Over C1, right? This means Cm is simply equal to the partition coefficient times C1. That's how we can relate these different concentrations, and this basically, it's a scaling factor to account for that discrepancy. In the end, they will be equal to each other with this scaling factor, okay? That's what it is, at equilibrium. So when you see it written in this way, it makes a little more sense, right? It's just a coefficient, right? It's a scaling factor for the differences in solubility. And we know the differences in solubility by the differences in the solute concentration in different solvents, okay? I hope you know your solvent versus solute by now, right? Okay, let's keep going. So then, right? So we know this, right? We know this. Then with that same logic, we also know when R is R out, we know that Cm is equal to the partition coefficient times C2, okay? So we know these two boundary conditions now. We know it because of the definition of the partition coefficient, okay? I just want to show you this one too, just to really solidify this concept. We know because what? We know because partition coefficient is equal to Cm over C2, right? And essentially, just move the C2 over, right? And you get this expression, okay? So we know our boundary conditions now. Now what are we doing with our actual, right, expression? We start with our very long conservation equation, but when we simplify to simply just diffusion, we have, right, our Laplacian operator, right, double del, right, or del squared, times our concentration, right, of the membrane, yeah, is equal to 0, right? It's a steady state. It's a steady state. And that means when we do cylindrical, right? So rectangular is another way, but when we do cylindrical, we know it's going to be 1 over R times d over dr times, or sorry, the derivative with respect to R of R times the derivative of concentration over with respect to R, right, is equal to 0. So of course, when we move the 1 over r, the 1 over r just cancels out to 0, right? We know that. Now, if we take the integral of both sides, right? Well, we're left with an expression. We have, right? And this cancels out. We have r times dcm dr is equal to a constant. And I'm going to, instead of using C1, C2, since we're using C's, I'm just going to use A, okay? A, B, C, D, E. This just a coefficient, okay? Or it's a constant, right? It's a constant, right? And remember, that's a sign for constant. So now that we have this, right, we can keep going. Well, then we can move the r over to the other side, right? Then we have the derivative of the concentration in the membrane with respect to r is equal to A over R, right? Take the integral of both sides. Hopefully we all know this by now. And we're left with an actual expression for the concentration profile, right? With respect to R is equal to A natural log R plus another constant, right? And remember, the constants are important. They are important because why? Because we use our boundary conditions to actually find those constants, okay? So let's list out our boundary conditions. So this is our general statement. We need to actually find some boundary conditions, right? Which we actually found above, okay? So I'm going to copy them straight from here and write them out right here. So we have at R equals Rn, right? Our first interface, right? We have the concentration of the membrane is the partition coefficient times the concentration of the inside, right? C1, at that interface, okay? This means, let's plug in partition coefficient C1 into this right here, right? Is equal to A, we don't know A, natural log of R in plus B, yeah? Now let's also do the same thing with our out. We know the concentration in the membrane is the partition coefficient times C2, right, at that interface. So that means we have, let's use the same color scheme. Partition coefficient C2 is equal to A natural log R out plus B, okay? And we need to basically solve for A and B. Well, I see an easy way to cancel out the B to solve for A first, right? And that's by just subtracting, right? Subtracting. So I'll write that out again. So we have C1, right? I'm just going to copy it from above, is equal to A natural log Rn plus B, and then minus this entire expression, okay? A natural log R out plus B, right? And we know this means the B minus B is 0, right? So, and then we have partition coefficient, we can pull that out, C1 minus C2, right? Partition coefficient C1 minus partition coefficient C2, right? Good. Is equal to, now here, we can pull out the A, right? A natural log R in minus A natural log R out. So we can pull out the A. Then we have natural log R in minus natural log R out. We know by our log rules, right? This, right? ln A minus ln B, right, is equal to ln A divided by B, right? We know this, right? This is one we should know. So with that, we can say, well, it's going to be A natural log R in divided by R out, okay? And this gives us already our first coefficient. Yay! We have our first coefficient of C1 minus C2 over natural log R in over R out. Okay? So we have our first A coefficient. Now, okay, what about our B? Well, let's actually use what we just found most recently right here. We're going to use this, and we're going to simply rearrange for B. Okay, so let me rewrite it out right here. We have this from our previous result. Partition coefficient C2 is equal to A natural log R out plus B. And right, we're going to isolate the B, so we're going to just move this over here to that side. So that gives us B is equal to partition coefficient C2 minus A natural log R out. And what we can do is plug this A into here, right? We can plug it in. Or we can pause, right, and realize, let's recall, our CM expression is A natural log, right, R plus B. And if we plug in B, we can see, right, if we plug this B into here, we can say, oh, well, there's an A that we can pull out, right? And if there's a minus natural log here, we can simplify things before plugging in this kind of monstrous expression, right? Let's save ourselves some ink, right? Or I guess some digital ink in my case. But let's go and write it out. So we have CMR. So before I'm plugging in anything, A natural log R, basically plus, we're going to plug in this partition coefficient C2, this expression right here, we're plugging it in, minus A natural log R out. And what does that give us? That gives us, well, that gives us CM, right? CMR is equal to A natural log R over R out, right? Remember we said, well, this minus natural log, right? And this natural log, we can combine it into this, yeah? And then plus partition coefficient C2. Wow, we simplified it all the way to here, right? We were like freaking out that this is going to be a very hard kind of cylindrical problem, but actually it does simplify out really nicely. Well, until we plug in A, right? But still, that looks really great. So therefore, we know that the concentration profile in the membrane is going to be, and I'm going to just simply copy this over here, right? I could just do this, just go like this, copy, and paste it. Yeah. Right? It's going to be A. Remember, this is A. This is A, right? Times our natural log of our R over R out, right? Plus partition coefficient times C2. We just derived the expression for the concentration profile in the membrane, okay? Boom. But keep in mind, note, okay? Note, we don't have information about the slope, right? Is it positive? Or negative? We don't know, right? We don't know. Why? We need to know the actual values, right? Of C1 and C2, right? Of C1 and C2. Remember, okay, I'm going to scroll up. If we knew that C1 was up here, right? And CM was down here, right? And if we knew C2, right, was here, right? Let me think about this. C2 is here, right? and CM is here, right? Then we can actually determine, well, it's going to be a negative slope. It's going to be a negative slope, right? But if we have C1 is here and C2 is up here, right? And based on what we know, right? If CM or C2 is here, right? Then, right, we can have a positive slope. We don't know. And CM would be, sorry, not here. That's not true. CM, right? Here, right? CM could be there, and it could be positive slope. We do not know because we don't know the information about C1, C2. So if you do know the information about C1, C2, make sure to denote that properly in your expression, okay? Now, here's the challenge for you, okay? Your task. After watching this, try in rectangular, okay? Try what we just did right here in rectangular coordinates, okay? It's going to be really good practice, and it's going to really solidify this concept for you, okay? And then, right, you just need to follow this derivation, okay? Follow this derivation. If you're getting stuck, just remember, start with your actual expression, right? There's only diffusion. So express that. There's only diffusion at steady state. Then derive it in rectangular coordinates. Find the boundary conditions in rectangular coordinates, plug them in, and solve for the expression for the concentration membrane profile, okay? If you can do that, you really do understand the power of partition coefficients. Let's remember, partition coefficients tell us about the solubility of the molecule in question in two different solvents, and that is it. It's not rocket science, okay? So don't be confused by this, and if you do have any questions after watching this video, please send me an email. I'm more than happy to help, but I hope you have a great rest of your day, and good luck on the upcoming exam. Wish you all the best of luck. You all are going to do so amazing, and I'm really proud of all of you. Thanks for watching, and see you next time.